Hello, my name's Ben Reinhardt. I'm project manager for a multi-state project called Transforming Drainage, which is a project that focuses on different practices that we can use in tile drained landscapes to increase water storage in agriculture. Now, today I'm going to talk specifically about the nutrient loss reduction potential of drainage systems which have the ability to capture, store, and reuse subsurface drainage water, which is a practice that we refer to as drainage water recycling. Now, historically, water storage has played a large role in the Midwestern landscape. Where seasonal excess water was commonly held on the landscape, there was opportunity for use, tie up of nutrients, or removal through various biophysical processes. However, as crop production intensified across the region, these areas of water storage required tile drainage to be able to support crop production, both in terms of farm management activities as well as avoidance of any stresses on the crop itself. However, this has come at a cost, and this cost has been an increase in nutrient delivery downstream, both in regards to nitrogen as well as phosphorus. Now, this has led to various local and regional efforts to find ways to curb that nutrient loss from tile drained agriculture. An example of this type of planning can be seen here with the Iowa Nutrient Reduction Strategy, which calls for a 41% reduction in nitrogen. However, when we look across the suite of practices that we have available to reduce nutrient loads, we can see quite a bit of variability in terms of effectiveness. Now, the graph shown here is for nitrogen reduction efficiencies. The same could be said for phosphorus reduction efficiencies. And the suite of practices will look a little different as well. So those practices that are highly effective at removing nitrogen may not be so at removing phosphorus. So ideally, in today's tile drained agriculture, we would have certain practices that are effective at both reducing nitrogen as well as phosphorus from the field, and can do so across a range of conditions and sites. Now, the practice of drainage water recycling represents a new vision of managing water in tile drain landscapes and has the opportunity to provide those water quality benefits for both nitrogen and phosphorus. Under this type of drainage system, water being transported from the field through subsurface drains is directed towards an on-farm water storage, such as a pond or a reservoir, where it is temporarily stored. Now, when water becomes limited in the field, water from the on-farm water storage is withdrawn and applied to the field in the form of irrigation. This practice helps to limit the leakiness of tile drain systems while also providing a crop production benefit and serving as a source of water for supplemental irrigation. But questions still remain in regards to how drainage water recycling can and should be designed. First, how much water storage is needed, particularly in relation to the size of the drained and irrigated area, to achieve either a crop-based irrigation target or a water quality-based target. And second, how will this relationship vary across changing climate and soil conditions? Now, with the analysis that I'll describe in a little bit, we focus primarily on the water quality goal to quantify nutrient reduction potential across various sizes of on-farm water storage. To explore this relationship, we estimated the balance of water between various components of the system. First, we described the primary water source for the on-farm water storage, which is daily drain flow. Also, we tracked soil water within the field, as this provides an estimate for when supplemental irrigation would be beneficial for crop growth. And last, we use information from components 1 and 2 to help track a daily water level and volume within the on-farm water storage. Now, in this analysis, daily drain flow was measured and served as an input, so the next few slides will focus on components 2 and 3. Looking first at soil moisture in the field, we needed to identify boundary conditions for that soil water storage. So we did this through 3 different terms. Now, first, through maximum soil moisture, we defined the total amount of water in the soil profile at saturation. Next, through total available water capacity, we define the amount of water held between field capacity and permanent wilding point. And last, we define a field area so that we can apply these quantities as volumes. We could then use these boundary conditions to specify irrigation events. Now in this case, once total available water capacity was depleted by 50%, we applied a 1-inch irrigation application from the on-farm water storage. Next, to construct the daily balance of soil water, we use 3 primary variables to help us track this. The first 2 are additions to the soil water reservoir, these being effective precipitation, or the portion of natural precipitation that doesn't run off or seep out of the root zone, and the irrigation applied. The last variable that we incorporate is a loss term, and this is represented by soil water loss due to evapotranspiration. So effectively, our equation for tracking daily soil water becomes effective precipitation plus any applied irrigation minus water loss through evaporation or transpiration by crops. Now in this analysis, we've referred to the FAO program ClimeWatt in establishing values for effective precipitation. The graph here shows long-term monthly averages of effective precipitation, estimated using the SCS curve number method and ClimeWatt. Now we converted these to monthly percent values and applied them to daily measured precipitation to estimate a daily effective precipitation. Next, for the evapotranspiration term in the equation, we estimated a grass-based reference ET from measured daily climate data based on FAO 56 methods. We then used crop coefficients that we pulled from the FAO program CropWatt for a maize crop to get a daily estimated ET. So now looking at the water storage component of the system, we again needed to identify physical boundary parameters. So first, in defining a maximum potential storage volume, we wanted to simplify pond geometry, just because this can vary widely based on what type of pond or reservoir it is. And so we characterize water storage by relative or average depth rather than a maximum depth. Next, to track the daily water levels and volumes in that on-farm water storage, we look at 5 variables. The first 2, again, are additions to the system, being drain flow as the primary input, and then also tracking precipitation contributions to the on-farm water storage. The last 3 variables are loss terms and are represented by evaporation from the water surface, irrigation withdrawals, and any seepage loss along the wetted face of the on-farm water storage. With these variables defined, the equation for daily pond volume becomes drain flow plus natural precipitation minus losses due to evaporation, water withdrawal, and seepage. We utilized measured daily data sets for both drain flow and precipitation inputs to the on-farm water storage. Open water evaporation values were estimated based on average monthly values from a National Weather Service pan on site, and seepage was held constant at 3 millimeters per day. So now let's visualize the results of this overall balance when drained water from the field is collected in the on-farm water storage. Now there are 2 potential scenarios that we tracked. First, if the available capacity within the water storage exceeds the volume of flow coming in, then that flow can be considered captured or stored. This scenario represents the primary opportunity for water quality benefit since nutrients are captured within the system. The second scenario would be when the available capacity is less than incoming flow. In this case, bypass or overflow would have to occur from the system and discharge is directed to an appropriate outlet, as would be the case in any conventional drainage system. Now when water is removed from the system for irrigation, again there are 2 potential scenarios that we considered. First, when there is adequate water stored to meet the targeted irrigation event, which again in this analysis we defined as 1 inch across the irrigated area, a full irrigation application was directed to the field. However, if that desired irrigation amount exceeded available volume within the water storage, whatever is available in the storage was applied, but ultimately a storage deficit existed since a full irrigation application could not be given. So now that we've defined both the capture and irrigation relationships of the drainage water recycling system, we look to apply this tool. We applied this tool to a drainage research site located at the Davis-Perdue Agricultural Center in East Central Indiana. This site hosts research plots evaluating free drainage and controlled drainage systems, and colleagues have utilized measured values to develop continuous daily data sets for drain flow, various weather data, and water quality concentration data. The annual drain flow for the Davis-Perdue Ag Center averaged 368 millimeters per year during the 10-year record. Monthly concentration values for nitrate, nitrogen, and total phosphorus are shown here as well. These monthly average values were applied to daily drain flow measurements to estimate nutrient loads moving through the drainage water recycling system. Now, since storage volume is expected to be one of the primary characteristics of defining potential benefits of the practice, both in terms for irrigation and water quality goals, this analysis set out to evaluate a range of storage sizes representing 2, 4, 6, 8, and 10% of the field area, each at an average depth of 3 meters. We used a drained and irrigated field area of 80 acres. So essentially in this case, 2% storage represents a 1.6 acre on-farm water storage. 6% storage represents a 4.8 acre on-farm water storage, and so on. Here's a picture of drainage water recycling in Michigan, which provides an example of what this variation in pond sizes would look like on the landscape. So in this case, on the left, we see a single 5 acre on-farm water storage, whereas on the right, these are older, smaller 1 acre water storages. So now let's look at some of the results. First, looking at results regarding the percent of annual drain flow that was able to be captured by the on-farm water storage. Again, this is the portion of flow that is captured and stored within the on-farm water storage. On this graph, as well as those following, we show the minimum, maximum, and then average values are indicated by the circles. So at 2% storage area, the average amount of drain flow captured was almost 20%. This increases to more than 50% capture on average for a storage area of 6%, and more than 80% on average for a storage area of 10%. Next, we calculated the portion of the nitrate-nitrogen load that could be captured and held within the system. Here on the left of the graph, in red, we see the normal background nitrate loading at the site. At 2% storage, we estimated that 5 kilograms per hectare, or only about 1/6 of the total average annual nitrate load, could be captured. However, as storage areas increase, so did the potential for capture, with nearly 50% capture on average at 6% storage area, and 75% capture at 10% storage area. Now, we saw similar results for the ability to capture and store phosphorus within the on-farm water storage. At 6% storage area, we estimated the ability to capture and store roughly half the total phosphorus average annual load at the site, and at 10%, this increases to 75% capture on average. So we can see there is some potential to implement drainage water recycling as a water quality practice for both nitrogen and phosphorus. But what about the other management goal of providing a water supply for supplemental irrigation? In this graph, the amount of desired irrigation, if water supply was unlimited for a corn crop at DPAC over the course of the 10-year period, is shown on the left in red. At 4% storage area, we estimated that the average applied irrigation would not be able to meet the average desired irrigation volumes at DPAC. However, this would be met given a storage area representing 8% of the field area. And at 10% storage area, we estimated the ability to meet the full range of irrigation demand at the site. But how might some of these results change in a different location? To begin exploring this question, we worked with partners at Iowa State University. Now note the differences in drain flow characteristics between the two sites. While average volumes are similar, there's a considerably wider range in measured volumes from the site in southeast Iowa. Now on the left, these are the same results that we've already seen from the DPAC site regarding the potential ability to capture drain flow volumes. This same analysis completed using data set from the southeast Iowa site shows notable differences, including a much wider range of effectiveness and an overall lower average effectiveness at larger storage volumes. Now this could potentially be attributed to the more variable flow conditions that we see within and across years, which are driven, at least in part, by different climate patterns and soil conditions. So to conclude, what did our analysis tell us about how large of an on-farm water storage is needed in a drainage water recycling system to offer water quality benefits? And here I refer back to the original graphic showing the ranges of effectiveness for various other water quality practices. So a pond that is on average 3 meters deep and covers 4% of the field area would provide an average nitrate reduction of just over 30%. That same pond, covering 6% of the field area, would have an average reduction of nearly 50%. So this would meet or exceed that target in most years of 40 to 45% reduction. And at 8%, we would see an average reduction of about 66%, indicating the ability to handle larger flow years and still reduce nutrient loss from tile drained areas. Now again, it's important to point out that these reductions were also similar for phosphorus. So next steps. We are planning to expand this analysis to elsewhere in the Midwest so that we can evaluate the relationship that different climates and soils have on drainage water recycling systems. And we're also working on developing a web-based tool that would be publicly available, allowing users to input their own daily drain flow, climate, and soil parameters and evaluate various sizes of on-farm water storage to meet either water quality or irrigation-based goals. With that, I want to thank you for listening to this presentation. Again, this work is part of a multi-state effort funded through the U.S. Department of Agriculture, National Institute of Food and Ag, and the project title is Managing Water for Increased Resiliency of Drained Agricultural Landscapes, or Transforming Drainage for short. You can find out more about the project at transformingdrainage.org and follow us on Twitter at @TD_drainage.